So this is EE698G. Lighting is lecture 17. So we are now looking at the relationship between the discrete time jitter sequence AK. For now we are considering a particular jitter definition of that of the absolute jitter, and the continuous time phase noise profile. So as before, we consider a square wave where we describe the square wave as some function of its total phase, where the total phase is of the form omega naught t plus some phase noise. Okay, so let me start with where we left off in the previous class. So we assumed an ideal clock. So the edges of the ideal clock are occurring at instances k minus 1 into t naught and k into t naught, where t naught is the time period of the clock wave. Then we have a real clock which is noisy, which means the edges are now going to be shifted with respect to the ideal edges. So let's say the edges are occurring like this. So this edge is occurring at some instant t k minus 1, and this is occurring at the instant tk. Then we plotted the total phase of both the signals. So the time points of interest are t k minus 1 and this is k minus 1 into t naught. Similarly, this corresponds to k t naught and this is tk. Right? Let me also mark 2 pi into k minus 1 and let's say this is 2 pi k. Now if the signal, the ideal total phase would go from k minus 1 t naught to k t naught, and in that span it has to cover a distance of 2 pi on the y-axis. Right? But the real clock will achieve 2 pi into k minus 1 at this instant because the edge is occurring there, and it will achieve 2 pi k at this instant. And we said that the waveform is expected to look something like this. Okay, so let me also extend this. And then I wrote the expression for total phase at the instant tk. Right? And what was that expression? So at tk, of course, the total phase is 2 pi k, and this will be equal to omega naught into, will it be kt naught? I am writing at the instant tk. So omega naught into tk plus the phase noise at tk. Right? Then I asked you to rearrange this and give me an expression for ak. Do you remember the expression? Please look at your notes and tell me. This was my n minus phi n tk by omega naught. Okay. So we derived the equation. The immediate next step to do is to do a sanity check. So can you tell me if it's dimensionally consistent?
Yes.
What is the dimension of the LHS?
4 seconds.
This is in seconds. RHS is also in seconds, right? So dimensionally this is fine. Does the negative sign make sense to you?
Time and phase are in reverse sign, right? If phase is more than.
So right now we are dealing with jitter. So
more the edges
advanced. So here we have defined our jitter to be positive if the edge is delayed. That's all. Right? So the negative sign also makes sense. Right? The only problem is this equation as such is not very useful to us, because if we knew the value of Tk, we would have directly done Tk minus Kt naught. So one quick suggestion I had gotten was to replace this as phi n of Kt naught. I think by now all of us are inclined to look for the closest value we know and then take that as the approximation, right? So let me bring a little more nuance to this discussion. I'm going to expand phi n of Tk and find out under what conditions this approximation makes sense. So this is phi n of Tk. This is phi n of, can you tell me this phi n of Tk in terms of Kt naught and any other number that you think is relevant? So I want to write it as phi n at some point. What should I write here? I just don't want to write Tk.
Kt naught plus something.
Kt naught plus something. What should that something be?
Tk minus Kt.
What is Tk minus Kt naught? It is correct, but what is Tk minus Kt naught? Ak. Right? So I can write this as Kt naught plus Ak. So the moment I see something like this, I am inclined to do a Taylor series expansion around Kt naught. Right? So this will be equal to phi n of Kt naught plus Ak into first derivative of phi n around Kt naught plus higher order terms which can be ignored if Ak is a small value to begin with. Now quickly rearrange this and give me an expression for Ak. So what is phi n of Kt naught? So give me an expression for Ak. We'll take it from there.
Phi n of Tk upon phi n of Kt naught minus 1
So this is phi n of
Kt naught. Sorry, Tk, sorry, Tk. Still it's in terms of phi and Kt naught, right?
So you can use this expression and this expression, and then can you simplify and give me an expression for Ak? Okay. So now, so earlier we were working with minus phi n of Tk by omega naught. Now we have one more term in the denominator. What comment can you make about this additional term? What does this represent? Derivative of phi n of Kt naught.
It's changing with time.
How? You can talk about it as instantaneous frequency, but in very layman terms, it tells you how fast phi n of t is varying around phi n of Kt naught, right? And for most signals that we'll deal with, this change is going to be very, very small. So small that it can be ignored compared to the omega naught.
Right, slope, right?
It is a slope.
But in the diagram we have seen the slope was around 45.
So the
45 degrees.
right. So how does this is the plot of the total phase,
How, sorry.
right? Now if I were to plot phi n of
That will
t,
be flat,
that is going to look like this, right?
Yeah.
So the assumption, so then if I say that phi n is varying very slowly around kt naught, then I can ignore this to be 0. And your expression simplifies to minus phi n of kt naught divided by omega naught. So let me clearly write down the assumptions we have made. So the first assumption we made was that ak, the absolute jitter value, is small. The second assumption is that phi n of t is varying very slowly around this kt naught over the duration of this ak. Right? So provided these two assumptions are valid, now you can say ak is equal to minus phi n kt naught by omega naught. Right? So now you have a relationship between absolute jitter, which is a discrete time sequence, and phase noise, which is a continuous time signal. And that relationship is ak is equal to minus phi n kt naught divided by omega naught. Right? So it is a sampled and scaled version. Jitter is a sampled and scaled version of the phase noise. So I can represent this as a model. So I take my phi n of t. I have to sample this. So this is sampled at kt naught. And then I scale it with minus 1 by omega naught. And this gives you the sequence ak. So this I can also represent as minus phi n of kt naught divided by 2 pi by t naught. Just replace the omega. This is okay? So then here is a homework for you. You have to derive an expression for the period jitter pk in terms of phi n of t. Right? Once you derive an expression, you also have to construct a model. Sorry? This is homework, not right. Okay, so now if phi n of t was a wide sense stationary process, then ak, which is just a sampled and scaled version, will also be a wide sense stationary process. Right? Then I can calculate its autocorrelation. And once you calculate the autocorrelation, it becomes very easy to calculate the power in the signal.
Can you repeat that?
So if phi n of t is a wide sense stationary, it's WSS. So let's say phi n of t is WSS, then AK sequence will also be WSS. So how do I calculate autocorrelation in phi n of t? Just give me the expression.
Expectation of phi n t mod of phi n t.
So let me call this as some R phi of tau. This will be equal to expectation of phi n of t into phi n of t plus tau. Right? R phi of 0 is the expression that you said. Right? So autocorrelation of the sequence AK, let's say this is some RA, the index has to be, it has to be an index, right? So let's say RA of M, this will be equal to expectation of AK into A of K plus M. Okay? So let's take RA of M. How do you think it relates to R phi?
It's 1 by omega naught square.
There should be a 1 by omega naught square.
And
What should I write on the numerator? It can't be R phi of tau.
It will end.
It has to be R phi of M into T naught. So you have the relationship between phi n and AK. So if you shift AK by some sequence, multiply and then take the expectation, you get RA of M. Right? That has to be related with the R phi of tau also as a sampled and scaled version. So this is the sampling, the scaling is now with 1 by omega naught square. Because you will have 2 omega naughts from here.
What does tau and m represent here?
So tau represents, so if I take xt, that is some signal, let's say like this. Let me take a, right? Now if I take x of t plus tau, where this tau can be varied, it simply means that I have taken this pulse with some delay or advancement. So I'm varying it with respect to that tau. Okay. Now when I talk about discrete time sequence, I can vary it only with respect to an index. The same signal, if I represent in discrete time sequence, it will look like this. Right? So now I take this, and if I am sliding it over the index, that index is m.
Isn't there all of the autocorrelation some integration?
It is. So expectation, then you replace it with the time average of these. Okay. Now, if I write the expression RA of 0, what does that mean?
Power of the jitter.
Power of the jitter sequence, right? So this is power of the jitter sequence. In other words, if it was a 0 main sequence, I can write it like this, right? So this is the power in AK. Now this will be equal to R phi of 0 divided by omega naught square, right? And what is R phi of 0?
Power of the phase.
Power of phase noise. And that I can find out by integrating the phase noise PFD and then dividing it by omega naught square. Do you think this result is useful?
What is S phi of M?
So if I have phi n of t and I take its PSD, that gives me S phi of f.
By this we can know the power in the AK, right?
Power in the, sorry.
In the AK we can know the power in AK, right?
Power in AK,
If
if you know phi n of t, you can know power in AK. But where do you foresee the usage of such a relationship? Basically integrating S phi of f and then calculating the power in jitter sequence.
It's hard to measure the individual jitters, so you just have the phase noise expression. You can get the jitter.
So that is what I'm looking at, but let me give you an example that you are very familiar with. Everyone now knows what a DLL is, right? You also know the relationship from the input of the DLL where you feed the reference. So let's say you had a small signal phi ref here. You know what is the relationship between phi ref to phi out. You know the transfer function, right? Now let's say the signal that you are giving here, so having a small signal phase noise, has a small signal phase noise phi ref, right? So then you can also calculate what is the PSD of this. Once you know the PSD of the input, you can calculate the PSD of the output. What is the expression? This will be equal to magnitude of h of f the whole square into S phi ref of f. Right? So just by knowing the PSD of the phase noise at the input of the DLL, now you can calculate the power in the jitter sequence at the output. Are you able to appreciate the effect? So typically we would have expected this h of f to be all pass transfer function, but we have derived it exactly, and we know that it has peaking. We just know that the peaking is happening for certain frequencies, right? Which means that if there was phase noise around those frequencies, those components alone are now going to get amplified. Right? So just by looking at the jitter sequence at the input, you might find it very difficult to predict how the jitter sequence is going to appear at the output. Right? But if you know the phase noise of the PSD of the phase noise at the input and the transfer function of the DLL, you can calculate the output phase noise PSD, and from there you can predict the properties of the jitter.
Shouldn't that be S phi n?
You are what are you calling as S? Acha, this one. Matter of convention. If you want to call it S phi n of f, we can call it S phi n of f.
Because once
Here.
I was thinking about phi ref is the signal that we are giving.
Phi ref, so
It's the phase of that clock signal that we
correct. If you are giving an ideal clock signal, right, the ideal clock signal will have some total phase. Right? So let me mention it with respect to t. If this was ideal, what would be the small signal phase in this? 0. Right?
So
So
signal thing is due to the noise.
small signal thing can also be due to noise. So here I just assumed that the small signal was the noise. There are cases where you intentionally introduce small signal phase, like in modulation. Right? If you know what exactly the small signal phase is, if it was not noise, which means you wouldn't call it as jitter per se. That is information that you need, right? So you might then it's a very deterministic input. You can directly multiply it with the transfer function and look at the Fourier transform at the output. If it was noise, then you don't know its behavior completely, so you multiply with the transfer function square and work with the power spectral densities. Okay, so
How will it be useful then? Because we are getting the noise power at the output.
you are getting the noise power, so you are getting the noise PSD at the output, right? Once you have the noise PSD, you can integrate it, divide it by omega naught square, and that will tell you what the power in the jitter sequence is at the output, right? And you take the square root of that, that is basically RMS jitter.
What exactly the power in the jitter signal?
Okay, so any signal you take, theoretically it is possible to calculate. It's a sequence of numbers. So you can calculate the RMS, you can calculate the power, etc. So now if you are interested so if you calculate the power, which means you can also calculate the RMS value. So that tells you, that is a way to quantize the jitter characteristic.
How much signal is consuming power and how much jitter is consuming?
It is not consuming the power in the sense that it's not consuming power from the battery separately, right? But it is a measure of how large the quantity is. Something with a larger RMS is, of course, has larger amplitudes also, right? And this is again sigma. So once you know sigma, you can look at whether it is within the 4 sigma or the 8 sigma constraint that you are working with. Okay, so let me remind you the top level picture that we are working towards. So if you have some V out as a function of t, which can be written, let's say, an ideal clock waveform of cos omega naught t plus phi n of t, right? Now you know that I take the phi n of t, I sample and scale it, I get AK. Right? It's a jitter sequence. Now, once you have AK, if you want, you can directly calculate what the power in the jitter sequence is directly based on the AK sequence, right? Or I can take the PSD of phi n of t. This gives you S phi n of f. Okay. Now, I can also take the PSD of V out, and this gives you S V out of f. Right? So I'll abbreviate this as SV of f so that it's easier to work with, right? Now I could also take the PSD of this jitter sequence, and this will give you a power spectral density for this, but it will be in terms of the discrete time frequency. Right? Ideally, we should be able to relate these two as well as these two. In time domain, we understand the relationship. So let's also try and understand how they will look like in the frequency domain. Now the conversion from S phi n of f to SA of e power j omega d is very simple if you know the sampling theorem. Now I understand a lot of you are not familiar with the sampling theorem, but we can't get into that now. So I'll give this as a homework for those of you who have seen this in DSP, right? See if you can figure out the relationship between SA of e power j omega d and S phi n of f. So this is not part of the syllabus now because most of you have not seen the sampling theorem.
In this is the expression, right?
No, then what? Where is the fun in that, right? You have to think what it will be, right? It's basic sampling theorem. So if you have an x of t, you can take its Fourier transform and get x of f, right? Now you can sample this and get x of k, right? And if I take the DFT, you will get some x of e power j omega d. So you know that the relationship between them is basically there is a scaling involved. You create replicas at every sampling frequency, and then you change the frequency x-axis, right? So this is what you do. So now the thing is, the Fourier transform that you are taking for is for the autocorrelation function. So R phi of tau is getting sampled and scaled to get R A of m. You take Fourier transform of this, you get S phi of f. You take the DFT of this, you get x of e power j omega d. Right? So how would you relate this is basically the question. Right? And the result is there in my last year's lecture. So if you want to verify, you can look at that. How many of you have done sampling theorem before? So DSP, mixed signal IC design, LPTV course. Mixed signal IC design some of you have done, right? In that you have dealt with sampling theorem. Yeah. Must have done an LPTV course also. Yeah. And DSP did not deal with sampling theorem? That's okay, perfectly valid. Okay, so now the only relationship remaining is to find out how SV of and S phi n of f is related, right? Can you think of any application where this S phi n of profile itself is very critical, more than the jitter sequence? Anytime we think of the clock, we are worried about how the edge is shifting, right? So do you think maybe there is an application where the profile of S phi n of f across frequency is more critical than just looking at the shifting of the edges?
When you need proper duty cycle.
When you need proper duty cycle, but again you are thinking in terms of the edges, right?
Okay. Yes.
Basically, when phi n of t is more critical than AK.
Basically, when phi n of t is more critical than AK, a reasonable answer. Is there a specific?
No, that translates to this thing, right?
That translates to. Okay, so let me give you an example, right? So the easiest thing you can think of as an example for this is a receiver chain. So the same applies for the transmitter chain as well. So the receiver chain has an antenna, then you have a low noise amplifier, right? And then you'll have a mixer, and then you will have some filtering action, followed by the ADC, right? Ideally, you would expect the signal being captured to have content around some carrier frequency, right? So you have some signal that is of interest to you, and then you provide the same carrier frequency through a local oscillator here, right? So this is some, let's say, A into cos of omega ct, right? Which means this has impulses at minus fc and plus fc. So you multiply them in time domain, therefore in frequency domain they need to be convolved, and what is the result you expect to see?
One bigger comparison.
So you'll have one at 0, then you'll also have something at minus 2 fc and plus 2 fc, which is why the filter is needed to subtract them. Now imagine, instead of having A cos omega ct, you had A cos omega ct plus some phase noise, right? And then intuitively we said that in the presence of phase noise, basically the power now has to spread around fc, right? So if you were looking at the PSD, instead of seeing impulses there, you would see something like this. Now if you convolve, you can clearly see the signal you get here is not just the information around the carrier. Even the phase noise of the clock is going to appear there. And the best way to see that is assume that the signal you are interested in were impulses to begin with, right? So the signal you get here is going to be the phase noise profile of the clock, of the local oscillator, right? That has basically corrupted the receiver action altogether, right? Depends on how wide the S phi of f is around fc, but it is corrupting what you expect to see. Now the problem becomes even more critical if you had a very strong blocker closer to fc, right? Another signal which was higher in power. Maybe something else was, you are trying to attend an interview in your hostel room and somebody else is having a family meeting in the other room, a Zoom call for it, right? So they are going to transmit a lot of power rather than the interviewer transmitting signals to you. So that becomes a blocker signal for you, right? So in the presence of blocker signal, now you will see a higher impulse, higher profile of this phase noise appearing around this frequency, right? Whatever this frequency is, around that you will see a larger signal. So now that is completely corrupting the information you wanted to receive. Okay, so this way the profile of S phi of f is also very critical in any scheme where modulation or mixing operation is involved. Okay, so now let us derive how S v of f and S phi of f are related. This relationship is one of the easiest relationship to derive. So we start with V of t being equal to A cos of omega naught t plus phi n of t. We expand this. Can you tell me the expression? So this is cos omega naught t cos of phi n of t minus sine of omega naught t into sine of phi n of t. Now we are going to make an approximation. We are going to assume that phi n of t is a very, very small number, much, much smaller than 1. Right? And this approximation is called as, do you know what this is called as? Small angle approximation, okay. But from communication systems, have you seen this being made? Narrow band FM approximation? So this is called as the narrowband FM approximation. So the moment I make this approximation, what does this reduce down to? Cos phi n of t. This becomes 1. This becomes phi n of t. Right? So this is equal to a cos of omega naught t minus a phi n of t into sine of omega naught t. Can you sketch the PSD for the signal? Let's say I take the PSD of this, I get some SV of f. Right? So now that is, the PSD is going to be summation of these two signals. How does this PSD look like?
It's a delta function.
It's a delta function. So at f naught and at minus f naught, this is a square by 4 and this is also a square by 4. Right? No confusions here. Let's say phi n of t had some profile which was given like this, some s phi of f with respect to f. What about this one? Same thing. Right? So this is again at f naught and minus f naught, a square by 4 and a square by 4. Right? So I have multiplied things in time domain. So you have to convolve, and what would it look like?
The same at f naught and minus f.
So
This will be
so you will have at f naught and at minus f naught. What would be the expression? Is it s phi of f?
S phi of f plus f naught f square.
No. So I want to know what I should write here for the shape.
F minus
So s phi of f minus f naught is when you wanted to shift it, right? Is there a scaling factor is my question. So this is a square by 4 into s phi of f, and this is also a square by 4 into s phi of f. Okay? So now sv of f,
The sign page, not wrong, one is below the.
correct. If you are taking the Fourier transform, I have taken the power spectral density.
Mod.
So yeah, square of whatever you have. You are looking at the magnitude square. So now you have a very nice way to plot SV of f. So you have impulses at a square by 4, impulses at f naught and at minus f naught. And then you get the scaled version s phi of f into a square by 4 appearing around it. So this is the two-sided SV of f. I can also plot the one-sided SV of f.
Is subtracting the second graph from the rows.
This is PSD, therefore they add in.
Okay, actually.
How does a one-sided SV of f look like? So around f naught, I have an impulse of value a square by 2, and you have s phi of f multiplied by a square by 2. Right? So let me also sketch the two-sided s phi of f here.
Here, S phi of f is assuming magnitude to be less than 1. right? That's why it's plotted below A square, right?
S phi of f, I've assumed the magnitude to be smaller than.
This is below
Right.
A square.
So this S phi of f was right. So this is the S phi of f shouldn't appear here. S phi of f is around 0. So this is the two-sided S phi of f. So what you have here is that the S phi of f has been shifted to f naught and scaled. That will give you the SV of f. We are trying to find the relationship between SV of f and S phi of f, right? So S phi of f has been scaled by the carrier amplitude and is shifted around the carrier frequency.
For making one-sided SVO.
So if whether I make it as one-sided or two-sided, I have to appropriately multiply it with the carrier amplitude. So if I'm making it as a two-sided PSD, I multiply it with by a square by 4. For one-sided PSD, I multiply it with by a square by 2.
So in this graph, like what I'm trying to make, like S phi of f in that two-sided.
So either of them, the result remains the same. So you can either look at the two-sided PSD or the one-sided PSD of SV of f. All that you have to do is take S phi of f, scale it by the carrier amplitude, right? And then shift it to f naught. So if you are looking at two-sided PSD, that scaling factor is a square by 4. For one-sided PSD, scaling factor is a square by 2. Okay. So now this is a very important information in lot of circuit design involving clocking circuits, right? And there is a very specific way for us to report it. So as you can clearly see, S phi of f has certain shape with respect to frequency. And in very layman terms, you can simply say this is the value of S phi of f for a given frequency, right? So there is a specific way to report these values. So the first step is to identify an offset frequency. Let me call that offset frequency as delta f. Okay. So what that means is you identify some delta f here. And this delta f will correspond to a delta f like this. Right? Which means you are actually in SV of f, you are looking at the point f naught plus delta f. Okay. So we are going to report phase noise based on the one-sided PSD of SV of f. So the first step is to identify the delta f. Okay. Once you have the offset frequency delta f, you calculate the power in a 1 Hz bandwidth at f naught plus delta f. So you look at the 1 Hz bandwidth here. So this is 1 Hz. And you calculate how much power is there in this band. Okay. And this is done for SV of f. What do you think the next step should be? So we are finally interested in the phase noise information, right? If you calculate the power in 1 Hz bandwidth at an offset frequency from f naught in SV of f, that number is scaled by the carrier power, right? So you normalize it to the carrier power so that the S phi of f information comes out. So normalize this power to carrier power. Right? Yeah.
Why does that 1 Hz is taken after f naught plus delta?
Where should it be taken?
can be taken before F0.
This is around F0 plus delta F. Right. 1 Hertz bandwidth around F0. So you are asking that F0 plus delta F should be right in the middle with 0.5 Hertz on either sides. Is that the? Yeah. That is.
What are you trying to do?
We are trying to report the phase noise of a clock. Right? And typically, how we would measure the phase noise is, in most cases, you will have a spectrum analyzer. And if you plug in the clock signal into the spectrum analyzer, then you will see the skirt around the clock, around the F0 frequency. Right? So the most common way to report the phase noise is by looking at the SV of F, the PSD of the voltage waveform, and then report L of F. Then report the phase noise. And how we typically do this is what I am describing here. So like I said, it's basically as if we are reporting the value of S phi of F for a given frequency. Right? But because this is a PSD, there is a particular way in which you have to report it. You have to take a small band around the delta if you are interested in, and then you report the power. So now there are specific instruments called as phase noise analyzers that can directly give you the S phi of F also. Right? So in which case you would directly look at the value at delta F and look at 1 Hertz bandwidth around it and then report that power. Okay. So you normalize this to the carrier power, and then the last step is to take 10 log 10 of this value. So the phase noise information is reported in units of dBc per Hertz. dB because you have taken 10 log 10. This C is standing for carrier. You have normalized it to the carrier power. Per Hertz because it is a PSD. It's a density function with respect to frequency. Now, how you write this value is L of delta F, right, where delta F is this offset frequency. So I can write the expression as 10 log 10 of a ratio. On the top side you have power in 1 Hertz bandwidth of SV of F at F equal to the carrier frequency plus the offset frequency. What is the denominator? Carrier power. Right? This is also same as 10 log 10 of S phi at delta F. Where this S phi of delta F, is it two-sided PSD or one-sided PSD? Or does it make a difference? Okay, so you said one-sided, right?
Otherwise, they have to get rid of the power in minus F0 minus delta.
So if it is one-sided, the one-sided PSD will be like this, right? You have to fold this around 0 and then you look at the one-sided PSD only for positive frequencies. But the one side, the two-sided S phi of F is now appearing at F0. Right? So it has to be two-sided PSD of S phi of F. So let's say I calculated some power here in this bandwidth. Right? This is what I am reporting as L of delta F here in this expression. So I am also writing it as 10 log 10 of S phi of delta F. So whether I calculate it from SV of F or from S phi of F, the power in that 1 Hertz band has to be same. Right? So now the question is, do I measure it here or do I measure it here? So this is a two-sided S phi of F. Let's say this is my one-sided S phi of F. How do I get the one-sided S phi of F? By folding it and adding, right? Which means the magnitudes here are going to be double. Right? So you need to have the two-sided. So this is a very important concept. Take a minute and see if you have any questions. Feel free to discuss. Because after you have convinced about the result, I want to confuse you with something.
Bottom line is we are trying to get the information of phase noise.
We are trying to get the information of phase noise. How do we, so if you have designed a clock signal, right, how do I report the phase noise information of that clock signal to somebody? Right, so what I would say is at 1 kilohertz offset, right, it has so much phase noise.
And that range is delta F here.
That the frequency that I'm mentioning is delta F, an offset frequency.
So in that way, how much is that phase noise we are reporting?
Correct. So typically, so let me give you an example. For a lot of applications, there are constraints, there are standards to be met, and that standards are written out in terms of saying you should have so much phase noise or better, or a lower number at certain offset frequencies. For example, if I were to take the GSM transmitter, right, so this has a carrier frequency at 900 megahertz. So how the specifications are mentioned is at delta F of 25 megahertz. So now it is at 925 megahertz. The phase noise spec has to be either minus 145 dBc per hertz or lower.
At 925.
So that is why the delta F is 25 megahertz. Right, so which means that exactly at 925 megahertz, the phase noise spec has to be either minus 145 dBc per hertz or lower. So this way, for different applications, there will be standards that you need to meet based on what can be the phase noise at certain offset frequencies. And similarly, when you design and when you are trying to compare multiple circuits, you either have this L of delta F plot versus frequency, or you compare it at certain offset frequencies. So you typically compare it, let's say 100 kilohertz, maybe 100 kilohertz, 1 megahertz, 2 megahertz, etc. These are the phase noise specs of my oscillator, my clock, but the phase noise specs of the other clock is so much, see, our clock is better.
Yeah.
Yes.
Should there be integration of S phi of F from delta F to delta F plus 1?
Where?
The second line of L of delta F.
Okay, I understand what you are saying. So you have to, so the PSD itself is power in 1 hertz bandwidth. Right, so
So small power and small bandwidth, something like that.
small power in, so there is, no, I didn't follow this thing.
PSD at a particular point should be a small power around that frequency.
Why do you say small power? It's a power around that frequency.
Around that frequency. It should be small because that frequency bandwidth is small.
It's okay, it is 1 hertz. Whatever is the power in that 1 hertz bandwidth, that is the.
But for example, if instead of 1 hertz we say 0.5 hertz, then should it be taken?
Then
we can normalize it with 0.5 hertz.
Yeah.
You can, then you have to clearly mention it because you are deviating from the standard definition. That's all.
But in that case, if we, for example, say we are taking from 0.5 hertz bandwidth, then shouldn't be integrating that?
Then you will have to integrate if you are reporting L of delta F. Simply because if you are reporting L of delta F, it's mostly because you are trying to meet a spec or you are comparing with another clock, right? So then the comparison has to be fair. That's all. So then you have to look at 1 hertz bandwidth. Is that okay? So everyone is very confident about this? No? You have doubts, or it's just that you need time to think about it?
Yes, I think.
That is
Not
okay.
right now.
Yeah. But let me then try and confuse you a little bit. So what do you think is the unit of S phi of F? So let's start with something simple. S V of F, what should be the unit?
Whole square. Whole square per hertz.
Volt square per hertz. Perfect. So now you can tell me what should be the unit of S phi of f.
Radian square per hertz.
Radian square per hertz. Everybody agrees? It is power. If let's say I had taken the Fourier transform of an angle, right, then it would be radian per hertz, right? So if I had taken some v of f, I had some voltage domain signal v of t, I took the Fourier transform v of f, then this has a units of volts per hertz. But because this is a PSD, the unit is volt square per hertz. Same reason, S phi of f is a PSD, therefore it has to be radian square per hertz.
This was the confusing question.
No, confusing question is coming now. Okay, so you have a relationship between S v of f and S phi of f now, right? I just want to make sure that it is dimensionally consistent. So I'm going to take you back to the expression we have derived.
Omega naught square naught.
So this expression,
Yes.
so the LHS was V out of t, right?
Yes.
What is the unit of this?
Volts.
What about this?
Volts.
What about this?
Volts. Pi of t is just a number without a
It's radian
no.
into,
No, kind of, because we did sine of t approximated to pi
Correct.
of t,
So
right?
we
So
did-
we removed that time we forced it to remove. We normalized it with the unit.
we didn't normalize it to the unit. Sine of phi n of t became phi n of t.
Sine of x we gave x when we.
Correct.
Correct.
So for the others who have not caught on yet, this you agree, the unit is radians into volt. There is phi n of t, there is a, therefore it has to be radians into volt. How can you be okay with an equation like this?
But we are approximating sine of something like x to be x.
Correct.
In that only it's not dimensionally correct, right? Because
So if it is dimensionally correct, we shouldn't be working with an expression like this, right? So how can we be okay with this inconsistency? Sorry?
It is not inconsistent, that's a numerical approximation.
That's a numerical approximation. It's
Right, so is it
not-
dimensionally consistent?
Yes.
yeah, so the radian should
That radian doesn't have, it's not there. right?
Radians, what is the dimension of radians?
X unit. There is nothing.
It's dimensionless. Do you remember how you defined an angle?
Because you always take sign of some dimensionless quantity, right?
Right. So do you remember the definition for radians? If you had an arc with length L and radius r, then the angle theta in radians is L by r. So radians is dimensionless. Therefore, you are not making any dimension. You don't have a dimensional inconsistency. Right. So that was the confusion I want to bring about. But I'm happy to see that nobody was confused. Okay. So now let me introduce you to another circuit, but at conceptual level now. So the circuit we are going to see is a voltage controlled oscillator. So in short, this is called as a VCO. So I'm going to draw parallels with the VCDL, which all of you are very familiar with. So in a VCDL, you have input, some output, and there is some delay across this given by TD, right? And you are able to vary this delay with respect to VC. And we were able to model this as this TD is equal to some T0 plus KDL into VC. Okay. So one way to construct this VCDL was to have variable elements, let's say tunable delay elements, and then I cascade enough of them, I can construct a variable delay line. Right. Now if I short and make a ring with odd number of elements, now when I change VC, delay of each unit will change, which means the frequency of oscillation will change. I put odd number of inverters in a loop, it is going to oscillate, right? And it's going to oscillate at some frequency, let's say f. Now as I change Vc, delay of the inverters change, because of which the frequency is changing. Now this becomes a voltage controlled oscillator, right? So we'll model this as a VCO. How many inputs do you think a VCO should have? What is that input? VC, right? You don't have to feed anything. It is able to generate the clock of its own, right? And then you have an output. And let's say I'm going to represent the frequency as some omega out. I can represent my omega out as some initial frequency omega naught plus some gain into Vc. Much like how I have written an expression here. So omega out is some omega naught into kVCO into Vc. So it's easy to visualize this in terms of a diagram. I am plotting the omega out versus Vc. There is some initial frequency omega naught and then a line like this where the slope is kVCO. Okay. Now I want to write the voltage domain expression for the signal here. Let me call this as V out. Let's say V out is equal to some cos of some total phase there as a function of time. Can you tell me how to replace this? So this is cos of something. You know the relationship between Vc and the frequency for a VCO. It has to be an integral. If you had the phase information, you calculated the instantaneous frequency by taking the derivative. So now if you have the frequency information, you have to integrate it to get the phase, right? So this expression becomes integral of omega out with respect to dt. So this gives you cos of omega naught t plus kVCO is a constant, it comes out into integral of Vc. Vc could be varying with time dt. This is okay?
The extra term kVCO into Vc.
Yeah.
You can call it an offset.
It depends on, so this Vc could be a function of time. We generally call something as offset if it is constant with respect to time. So the term kVCO into Vc need not be a constant. It can vary. Yeah.
Omega out will vary linearly.
Omega out that is a very good question. So much like in VCDL, the actual plot is going to be non-linear, right? But for modeling purposes, so the plot could be something like this, right? But for our analysis purposes, you are going to linearize it around the operating point. And once you linearize it, you can work with an expression like this. Now, if Vc was a constant Vc naught, then the point that you mentioned, this simply becomes an offset. It will become some omega naught plus kVCO into Vc naught into time. It becomes a frequency offset. So now let's go through some sample problems to get used to the circuit, right? So we'll do this together. Let's say the Vc of t is given by some Vm into cos of omega mt. Can you find expression for V out of t? So why don't you try this first? So you should have gotten the expression V out of t equal to A into cos of omega naught t plus kVCO into integral of Vc of t, which becomes Vm into cos of omega mt dt. right? So Vm is a constant, it comes out of the integral. Then you are integrating cos of omega mt, so that gives you sine of omega mt divided by omega. Okay. So then the next part is calculate peak to peak jitter in V out of t.
So we are trying to actually measure the range of the x-axis, like how much maximum jitter we are trying to.
That is what we are trying to measure, right? So I can write the total phase of the signal as some omega naught t plus kVCO Vm divided by omega m into sine of omega mt. Right? Now this is your operating point. This is the ideal the waveform that is linearly increasing with respect to omega naught, which forms your operating point. So this additional quantity here is what we generally would have called as phi n, right? Phi n if this was completely random in nature, right? Another term for this additional small signal is also phi x for excess phase. And the reason why sometimes we don't call this as phi n is when you have an oscillator like this, you might intentionally vary the Vc to obtain certain modulation at the output. This is not a noise, this is very intentional. So then you can call it as an excess phase, or you might even call it as small signal phase, etc. But typically you either call it as phase noise or simply the excess phase. Okay. So now in this particular case, because this is very intentional, I'll go ahead and simply call it as the excess phase. Okay. Now can you tell me what is the peak value for the excess phase? That is kVCO Vm divided by omega m. So what would be the peak to peak value? Twice of this. So now if you have peak to peak value of excess phase, what would be the peak to peak value for the jitter? This divided by omega naught, right? So that is 2 times kVCO Vm divided by omega m into omega naught. Okay. Now last part of this question. Can you calculate Fourier transform of V out of t? Basically show me how the it will be with respect to frequency. Plot it, right? You can make an assumption. You can assume that kVCO Vm divided by omega m is much smaller than 1 radius. So we'll discuss this in the next class. Thank you.